Today's video lecture is Introduction to Environmental Chemistry. Dear new and returning subscribers, welcome to the official YouTube channel of Triune Biblical University Global Extension, USA. We are thrilled to have you as part of our growing academic community. Whether you're a new subscriber or a returning viewer, we're excited to share our world-class education with you. Today, you are about to embark on an enlightening lecture designed to deepen your understanding. Understanding Environmental Chemistry. Exploring chemistry's role in environmental issues. Overview of environmental chemistry. Environmental chemistry studies the chemical processes occurring in the environment, helping us understand pollution and sustainability. Basic chemistry concepts. Understanding basic chemistry concepts is essential for grasping environmental processes and their impacts on ecosystems. Atmospheric and water chemistry. We will explore how atmospheric chemistry affects climate and weather, and the importance of water chemistry for ecosystems. Soil chemistry and pollution. The discussion will include soil chemistry and how pollution affects soil health, impacting agriculture and ecosystems. Chemical processes in environment. Environmental chemistry studies the various chemical processes occurring in the environment and their impacts on ecosystems. Impact on living organisms. Understanding how chemical processes affect living organisms is crucial for assessing ecological health and biodiversity. Interdisciplinary approach. Environmental chemistry integrates concepts from chemistry, biology, and environmental science to solve ecological issues effectively. 1. Environmental chemistry. Environmental chemistry is the study of the chemical processes that take place in the environment and how they influence both natural and human-made systems. These processes include chemical reactions between air, water, soil, and living organisms, such as those involving nutrients, minerals, and pollutants. Environmental cycles, like the carbon cycle, nitrogen cycle, and water cycle, which are driven by various chemical interactions. Pollution pathways, understanding how chemicals from human activity, e.g., industrial waste, agricultural runoff, or vehicle emissions, enter and move through the environment. Environmental chemists study how chemicals disperse in different environmental media, air, water, soil, their transformations, degradation, accumulation, or conversion, and their persistence over time. This helps us understand how substances like heavy metals, pesticides, and greenhouse gases interact with natural systems. 2. Impact on living organisms. The chemical processes in the environment can have significant effects on living organisms, from microbes to plants and animals. This is an area of intense study because pollution, toxic chemicals, such as heavy metals, e.g., mercury, lead, pesticides, and industrial chemicals, can accumulate in living organisms and disrupt biological functions. This is known as bioaccumulation and biomagnification. Health risks. Certain chemicals, like endocrine-disrupting compounds, can interfere with hormonal systems in both wildlife and humans, leading to reproductive and developmental issues. Climate change. Greenhouse gases, e.g., CO, methane, trap heat in the atmosphere, leading to global warming. This affects ecosystems and biodiversity, disrupting habitats, food chains, and species survival. Ecosystem services. Chemicals in the environment can impact ecosystem services such as pollination, soil fertility, and clean water. For example, nutrient pollution, e.g., excess nitrogen or phosphorus, can cause eutrophication, leading to oxygen depletion and fish kills in aquatic ecosystems. By studying how chemical substances affect organisms, we can assess ecological health, predict the consequences of chemical exposure, and devise strategies to protect biodiversity. 3. Interdisciplinary approach. Environmental chemistry is a highly interdisciplinary field that draws from multiple scientific domains to tackle complex environmental issues. Key contributions include: chemistry provides the foundational knowledge about molecular structures, chemical reactions, and environmental contaminants. Environmental chemists use techniques such as chromatography and spectroscopy to analyze chemicals in air, water, and soil. Biology helps in understanding how chemicals interact with living organisms at the cellular, organismal, and ecosystem levels. For example, studying how certain chemicals impact the genetic material of organisms or how pollutants are absorbed by plants and animals. Environmental science provides the broader context of ecosystems and environmental issues. It looks at how human activities affect the environment, assesses the ecological risks of chemicals, and formulates policies for environmental protection. Ecology works with environmental chemistry to understand how chemical changes in the environment influence biodiversity and ecosystem processes, such as nutrient cycling, predator-prey dynamics, and habitat quality. The integration of these disciplines is essential for addressing multifaceted problems like climate change, water pollution, and the loss of biodiversity. For example, when studying the effects of a chemical pollutant, an interdisciplinary approach might involve: 1. Chemical analysis to identify the pollutant. 2. Biological studies to examine its toxic effects on organisms. 3. Ecological studies to predict how these changes will impact ecosystems. 4. Policy and management strategies to mitigate or prevent harm. This collaborative framework is critical for developing sustainable solutions to environmental problems. Great! Let's look at some real-world case studies where environmental chemistry has been applied to solve environmental problems. These examples will showcase how an interdisciplinary approach, involving chemistry, biology, and environmental science, has been crucial for addressing global challenges. 1. The case of acid rain, environmental chemistry and biology and ecology. Issue: acid rain is a form of pollution caused by the release of sulfur dioxide, SO, and nitrogen oxides, NO, into the atmosphere, primarily from burning fossil fuels in power plants and vehicles. These gases combine with water vapor in the atmosphere to form sulfuric and nitric acids, which then fall to the earth as acid rain. Chemistry: the chemical reactions that produce sulfuric acid, HSO, and nitric acid, HNO, are well understood. These acids lower the pH of rainwater, making it more acidic. Biology: acid rain can damage plant tissues, reducing the ability of plants to photosynthesize. It can also directly affect aquatic organisms by lowering the pH of water bodies, making it difficult for species like fish to survive. Ecology: acid rain disrupts entire ecosystems, especially in forested areas and aquatic systems, causing a decline in biodiversity. Solution: governments and industries implemented regulations to reduce sulfur and nitrogen emissions, such as the U.S. Clean Air Act and international treaties like the Kyoto Protocol. The chemical understanding of acid formation and its biological consequences led to policy changes and the development of cleaner energy technologies, e.g., scrubbers on smokestacks, cleaner fuels. To the ozone hole, environmental chemistry and atmospheric science and policy. Issue: the depletion of the ozone layer, primarily caused by chlorofluorocarbons, CFCs, led to a significant hole in the ozone layer over Antarctica. The ozone layer is essential for protecting life on Earth from harmful ultraviolet, UV, radiation. Chemistry: CFCs, which were used in refrigerants and aerosol propellants, release chlorine atoms in the stratosphere. These chlorine atoms break down ozone molecules, O, reducing the ozone layer's ability to absorb UV radiation. Biology: increased UV radiation can cause DNA damage, leading to higher rates of skin cancer, cataracts, and other health issues in humans and animals. It also disrupts the growth of plankton, which is the base of the ocean food chain. Atmospheric science: scientists studied the chemical reactions and atmospheric dynamics that caused ozone depletion, leading to the realization that CFCs were the primary culprits. Solution: the Montreal Protocol, signed in 1987, was an international treaty to phase out the production of ozone-depleting substances like CFCs. Thanks to this coordinated effort, the ozone layer has started to recover, showcasing how understanding the chemical processes and their biological impacts can lead to effective global action. 3. The Exxon Valdez oil spill, environmental chemistry and biology and ecotoxicology. Issue: in 1989, the Exxon Valdez oil tanker spilled approximately 11 million gallons of crude oil into Prince William Sound, Alaska, causing extensive damage to marine and coastal ecosystems. Chemistry: oil contains complex hydrocarbons that are toxic to marine life. The chemical composition of the crude oil determined how it spread and how long it persisted in the environment. Some of the chemicals in the oil, like benzene and toluene, are carcinogenic and pose serious health risks. Biology: marine organisms, including fish, birds, and invertebrates, were exposed to the oil, which disrupted biological processes. Oil ingestion caused liver damage and reproductive failures in many species. Ecotoxicology: environmental chemists and biologists studied the toxic effects of the oil on local species and ecosystems. This interdisciplinary approach was key in assessing the long-term damage and identifying recovery strategies. Solution: cleanup efforts, such as using dispersants and bioremediation techniques, introducing microorganisms that degrade oil, were employed. Over time, policy changes were made to improve oil spill prevention and response strategies, emphasizing the need for better chemical tracking and risk management. For the Clean Water Act, environmental chemistry and public health and policy. Issue: in the mid-20th century, many water bodies in the United States were polluted by industrial waste, agricultural runoff, and untreated sewage, leading to public health concerns and ecosystem degradation. Chemistry: scientists studied the types of pollutants, heavy metals, pesticides, nutrients like nitrogen and phosphorus, and their chemical properties to determine how they contaminate water sources and affect aquatic life. Public health: polluted water contains pathogens, toxic metals, and chemicals that can cause diseases such as cholera, dysentery, and cancer. Protecting water quality is critical for public health. Policy: The Clean Water Act, 1972, set regulations for wastewater treatment and established standards for water quality. It helped reduce pollutants entering rivers, lakes, and streams, improving both ecosystem health and human health. Solution: the implementation of wastewater treatment facilities and stricter pollution control measures resulted in cleaner water, reduced public health risks, and better protection for aquatic species. Advances in analytical chemistry also made it easier to detect pollutants and enforce water quality standards. 5. Climate change and greenhouse gases, environmental chemistry and climate science and policy. Issue: the rise in atmospheric greenhouse gases, particularly carbon dioxide, CO, methane, CH, and nitrous oxide, NO, is contributing to global warming, with widespread consequences for the climate, ecosystems, and human society. Chemistry: understanding the chemistry of greenhouse gases, how they absorb and emit infrared radiation, was central to understanding how human activities, such as burning fossil fuels, contribute to global warming. Climate science: climate models integrate chemistry, physics, and biology to predict the impacts of increased greenhouse gases on global temperatures, weather patterns, and sea levels. Policy: international agreements like the Paris Agreement aim to limit global temperature rise by reducing greenhouse gas emissions, based on scientific evidence of their chemical effects on the atmosphere. Solution: efforts to reduce emissions, such as promoting renewable energy, increasing energy efficiency, and implementing carbon capture technologies, are all part of the global strategy to mitigate climate change. Environmental chemists continue to develop new methods to measure and reduce emissions while advocating for sustainable practices. Pollution control. Environmental chemistry provides essential insights for developing strategies to control and reduce pollution levels in various ecosystems. Resource management. Understanding chemical interactions aids in better resource management, ensuring sustainable use of natural resources for future generations. Green technologies. Environmental chemistry fosters the development of eco-friendly technologies that minimize environmental impact and promote sustainability. Air quality monitoring. Environmental chemistry plays a crucial role in assessing and improving air quality through various monitoring techniques. Water quality management. The field focuses on monitoring and managing water quality to ensure safe drinking water and healthy ecosystems. Waste management strategies. Environmental chemistry contributes to effective waste management strategies, promoting recycling and reducing environmental impact. Ecosystem chemical reactions. Studying chemical reactions within ecosystems is essential for understanding environmental changes and promoting restoration efforts. Let's begin. Point 1. Introduction to environmental chemistry. 1. Introduction to environmental chemistry. Environmental chemistry is the study of the chemical processes occurring in the environment, including interactions between natural and anthropogenic, human-made substances. This field is crucial for understanding how chemicals affect ecosystems, human health, and the planet as a whole. It involves studying the behavior, distribution, and fate of chemicals in air, water, soil, and living organisms. 1.1 Overview of environmental chemistry. Environmental chemistry focuses on understanding how chemical substances interact with the environment. These interactions include how pollutants are released into the air, water, and soil, how they are transformed, and how they move through the environment. Environmental chemists also study the impact of chemicals on living organisms and ecosystems. This includes both harmful substances, such as toxins, and beneficial substances, like nutrients that sustain life. The study of environmental chemistry includes several key concepts. Chemical reactions in the environment. Chemical cycles, such as the nitrogen and carbon cycles. Toxicology, which examines the harmful effects of chemicals on living organisms. The movement of chemicals through the environment, or FATE, and transport. 1.2 Importance of environmental chemistry in sustainability. Author, Triune Biblical University Global Extension, USA. www.tbuglobalextensionusa.com. Environmental chemistry plays a critical role in sustainability because it helps us understand how human activities affect the environment and how we can mitigate negative impacts. Some key contributions to sustainability include pollution control. Environmental chemistry helps in identifying and controlling pollutants, e.g., greenhouse gases, heavy metals, pesticides, to reduce their harmful impact on ecosystems and human health. Waste management. Through chemical analysis, we can develop methods to treat and recycle waste, reducing contamination of land and water resources. Green chemistry. This subfield emphasizes designing chemicals and processes that are environmentally friendly, using renewable resources, and minimizing waste and energy use. Climate change. Understanding the chemical interactions contributing to climate change, like greenhouse gas emissions, is essential for developing strategies to reduce global warming. Sustainability depends on balancing the demands of human activity with the health of the natural environment. Environmental chemistry provides the tools and knowledge necessary to manage and conserve natural resources, reduce pollution, and ensure environmental protection. 1.3 Scope and applications of environmental chemistry. The scope of environmental chemistry is vast and interdisciplinary, encompassing a wide range of scientific fields and applications. Water quality management. Environmental chemistry is crucial in assessing water pollution, determining water treatment strategies, and ensuring safe drinking water. Air pollution. The study of chemical pollutants in the atmosphere, such as particulate matter, ozone, and sulfur dioxide, is central to mitigating air quality issues. Soil contamination. Chemicals that pollute the soil can affect agricultural productivity and harm ecosystems. Environmental chemists work to identify these contaminants and develop remediation methods. Environmental monitoring and analysis. Techniques such as chromatography and spectroscopy are used to detect and quantify pollutants in air, water, soil, and biological tissues. Remediation technologies. Environmental chemists develop and apply methods to clean up polluted environments, including bioremediation, using living organisms to remove pollutants, and chemical treatments. Through these applications, environmental chemistry contributes to a cleaner, healthier environment and helps address the challenges posed by pollution, climate change, and resource depletion. Chemical reactions in the environment. Chemical reactions in the environment are crucial processes that affect air quality, climate, and overall ecosystem health. These reactions can be classified into several categories, including photochemical reactions, redox reactions, and acid-base reactions. Each type plays a significant role in shaping the atmospheric composition and influencing environmental conditions. 1. Photochemical reactions. Photochemical reactions occur when sunlight drives chemical transformations in the atmosphere. A prime example is the formation of ground-level ozone, O, which results from the reaction between volatile organic compounds, VOX, and nitrogen oxides, NO, in the presence of sunlight. This process is particularly prevalent in urban areas where vehicle emissions contribute to elevated levels of these precursors. Ground-level ozone is a harmful pollutant that can cause respiratory issues and damage vegetation. 2. Redox reactions. Redox, reduction oxidation, reactions involve the transfer of electrons between substances, leading to changes in oxidation states. In environmental chemistry, redox reactions are vital for processes such as the degradation of pollutants and nutrient cycling. For instance, the oxidation of sulfur dioxide, SO, to sulfate, SO superscript 2, contributes to acid rain formation, which can harm aquatic ecosystems and terrestrial plants. 3. Acid-base reactions. Acid-base reactions play a significant role in regulating pH levels in natural waters and soils. The interaction between carbon dioxide, CO, and water, HO, forms carbonic acid, HCO, which can lower pH levels in aquatic systems, affecting aquatic life. Additionally, acid deposition from human activities can lead to soil acidification, impacting plant growth and nutrient availability. 4. Impact on air quality. Chemical reactions significantly influence air quality by producing or removing pollutants from the atmosphere. For example, secondary pollutants like particulate matter can form through complex atmospheric chemistry involving precursor gases emitted from industrial activities and vehicles. Understanding these chemical processes is essential for developing strategies to mitigate air pollution. 5. Climate change interactions. Many chemical reactions also interact with climate change dynamics. The release of greenhouse gases such as carbon dioxide, CO, and methane, CH, through combustion processes contributes to global warming. Conversely, certain chemical reactions can help sequester carbon or reduce greenhouse gas concentrations through natural processes like photosynthesis or engineered solutions like carbon capture technologies. In summary, chemical reactions in the environment are diverse and interconnected processes that significantly impact air quality, climate change, and ecosystem health. Understanding these reactions is critical for addressing environmental challenges effectively. Chemical reactions in the environment. Chemical cycles, such as the nitrogen and carbon cycles. Chemical cycles. Chemical cycles, also known as biogeochemical cycles, are essential processes that describe the movement and transformation of chemical elements and compounds between living organisms, biotic components, and their non-living environment, abiotic components. These cycles ensure that vital nutrients are recycled within ecosystems, supporting life on Earth. The primary chemical cycles include the carbon cycle, nitrogen cycle, water cycle, phosphorus cycle, sulfur cycle, and others. 1. Carbon cycle. The carbon cycle is a fundamental process in which carbon atoms are exchanged among the biosphere, geosphere, hydrosphere, and atmosphere. It begins with photosynthesis, where plants absorb atmospheric carbon dioxide, CO2, and convert it into organic compounds. These compounds serve as energy sources for various organisms through consumption. Carbon is then returned to the atmosphere via respiration by animals and plants or through decomposition when organisms die. Additionally, human activities such as burning fossil fuels release stored carbon back into the atmosphere, contributing to climate change. 2. Nitrogen cycle. The nitrogen cycle involves the transformation of nitrogen in various forms through biological processes. Atmospheric nitrogen gas, N2, is converted into ammonia, NH3, by nitrogen-fixing bacteria in a process called nitrogen fixation. This ammonia can be further transformed into nitrates, NO3, that plants can absorb and utilize for growth. When animals consume these plants or other animals, they incorporate nitrogen into their bodies. Eventually, nitrogen returns to the atmosphere through denitrification processes carried out by specific bacteria. 3. Water cycle. The water cycle describes the continuous movement of water on Earth through evaporation, condensation, precipitation, infiltration, and runoff. Water evaporates from oceans and land surfaces to form clouds in the atmosphere. Precipitation occurs when clouds release water back to Earth's surface in forms such as rain or snow. Some of this water infiltrates the ground to replenish groundwater supplies, while some flows over land surfaces into rivers and oceans. 4. Phosphorus cycle. The phosphorus cycle involves the movement of phosphorus through rocks, soil, water bodies, and living organisms. Unlike carbon or nitrogen cycles that have a gaseous phase, phosphorus primarily exists in solid form within minerals found in rocks. Weathering releases phosphate ions into soil and water systems where they can be absorbed by plants. Animals obtain phosphorus by consuming these plants or other animals. After death or excretion, phosphorus returns to soil or sediments. 5. Sulfur cycle. The sulfur cycle describes how sulfur moves between rocks, waterways, living organisms, and the atmosphere. Sulfur exists mainly in sedimentary rocks but can also be found in Author, Triune Biblical University Global Extension, USA. www.tbuglobalextensionusa.com. Minerals like gypsum or pyrite. Biological processes such as decomposition release sulfur back into soils as sulfates, SO4,2, which plants can use for growth. Sulfur is also released into the atmosphere from volcanic eruptions or human activities like burning fossil fuels. 6. Importance of chemical cycles. Chemical cycles are crucial for maintaining ecosystem health and stability because they regulate nutrient availability for organisms at all trophic levels: producers, plants, consumers, animals, and decomposers, fungi/bacteria. Disruptions to these cycles due to human activities such as pollution or deforestation can lead to environmental issues like climate change or biodiversity loss. In summary, chemical cycles represent interconnected pathways through which essential elements circulate within ecosystems, ensuring life sustains itself over time. 1. Chemical cycles, such as the nitrogen and carbon cycles. Toxicology, which examines the harmful effects of chemicals on living organisms. Toxicology. Toxicology is a scientific discipline that focuses on the study of the adverse effects that chemical substances can have on living organisms, including humans, animals, and the environment. It encompasses a wide range of topics, including the identification of toxic substances, understanding their mechanisms of action, and assessing their potential health risks. The field has evolved significantly over time, transitioning from a focus primarily on poisons to a broader emphasis on safety and risk assessment. Key concepts in toxicology. 1. Dose-response relationship. One of the fundamental principles in toxicology is the dose-response relationship, which describes how the severity of an effect is related to the amount, dose, of a substance that an organism is exposed to. This principle highlights that not all exposures result in harm, rather, it is often the quantity and duration of exposure that determine whether adverse effects will occur. 2. Factors influencing toxicity. Several factors influence how a chemical affects an organism. Dosage. Higher doses are generally more likely to cause harm. Duration of exposure. Acute exposure, short-term, may have different effects compared to chronic exposure, long-term. Route of exposure. The way a substance enters the body, inhalation, ingestion, dermal contact, can affect its toxicity. Biological factors, age, sex, genetic predisposition, and overall health can influence individual susceptibility to toxins. 3 types of toxicants. Toxicologists study various types of toxicants including environmental pollutants, pharmaceuticals, industrial chemicals, and naturally occurring toxins, e.g., those found in certain plants or animals. 4 applications of toxicology. The knowledge gained from toxicological studies is critical for public health and safety. It informs regulatory agencies in setting safety standards for chemicals in food, water, air quality, and consumer products. Additionally, it aids pharmaceutical companies in developing safer drugs by understanding potential side effects. 5 emerging areas in toxicology. Recent advancements include research into chemical mixtures and their cumulative effects on health, as well as the development of new models for predicting toxicity based on biological data rather than traditional animal testing methods. 6 Professional certification. toxicologists may obtain certifications such as Diplomate of the American Board of Toxicology, DABT, indicating their expertise and commitment to maintaining high professional standards within the field. In summary, toxicology plays a crucial role in safeguarding human health by providing essential information about harmful substances and guiding policies aimed at minimizing exposure risks. The movement of chemicals through the environment, or FATE, and transport. FATE and transport of chemicals in the environment. The movement of chemicals through the environment, often referred to as FATE and transport, is a critical concept in environmental science that describes how contaminants behave once they are released into various environmental media. This process encompasses several key components. 1. Definition of FATE and transport. FATE refers to what ultimately happens to a contaminant after its release. This can include physical, chemical, or biological transformations, accumulation in certain media, or degradation into less harmful substances. Transport involves the movement of contaminants through different pathways such as air, water, and soil. This movement can be influenced by natural processes like wind and rain, as well as human activities. 2. Mechanisms of movement. Contaminants can migrate from their source through various mechanisms, including leaching into groundwater, runoff into surface water bodies, or volatilization into the atmosphere. The specific pathways depend on the properties of the contaminants, e.g., solubility, volatility, and environmental conditions, e.g., soil type, climate. 3. Persistence of contaminants. Persistence refers to how long a contaminant remains in the environment before it degrades or transforms into other substances. Some chemicals may persist for extended periods due to their stability under environmental conditions, while others may degrade rapidly. 4. Factors influencing FATE and transport. Several factors influence how contaminants move and change in the environment. Physical properties, characteristics such as molecular weight, solubility, and vapor pressure affect how a chemical behaves. Environmental conditions, climate factors, temperature, precipitation, topography, land slope, and biological activity all play roles in determining contaminant behavior. Chemical reactions. Contaminants may undergo reactions that alter their form or toxicity, e.g., biodegradation. 5. Importance of FATE and transport studies. Understanding FATE and transport is essential for assessing potential risks to human health and ecosystems. It helps determine who might be exposed to contaminants and informs remediation strategies. Evaluations often rely on qualitative assessments rather than complex quantitative models unless specific site conditions warrant detailed analysis. 6. Research applications. Research on FATE and transport informs regulatory decisions regarding environmental protection measures. For example, studies help identify where sampling should occur to characterize contamination levels effectively. In summary, understanding the FATE and transport of chemicals is crucial for evaluating environmental contamination risks and developing effective management strategies. Atomic and molecular structures. Atomic and molecular structures form the foundation of chemistry, essential for understanding more complex chemical interactions. Chemical reactions. Chemical reactions are processes that transform substances, fundamental to all chemical phenomena, including environmental impacts. Thermodynamics. Thermodynamics studies energy transformations in chemical processes, crucial for understanding environmental chemistry and energy flow. Kinetics. Kinetics focuses on the rates of chemical reactions, helping to understand how fast environmental processes occur. Building blocks of matter. Atoms and molecules form the essential components of all matter, making them crucial for understanding chemistry. Interactions of substances. Understanding atomic and molecular structures reveals how substances interact within various environments, influencing reactions. Chemical reactions. Knowledge of atomic and molecular structures is essential for comprehending and predicting chemical reactions and processes. Understanding chemical reactions. Chemical reactions involve the transformation of substances through the formation and breaking of chemical bonds. Types of bonding. Identifying different types of bonds such as ionic and covalent is essential for understanding chemical interactions. Environmental chemical processes. The study of bonding types is crucial for understanding various environmental chemical processes and their implications. Point 2. Basic concepts in chemistry. 2 basic concepts in chemistry. Understanding the fundamental concepts of chemistry is crucial for environmental chemistry. These concepts provide the foundation for analyzing how chemicals behave in the environment and their impact on ecosystems, human health, and the climate. Below are the core concepts in chemistry that are key to environmental chemistry. 2.1 Atomic and molecular structure. Atoms are the basic building blocks of matter, consisting of a nucleus made of protons and neutrons, surrounded by electrons in orbitals. The arrangement and behavior of these atoms determine the chemical properties of substances. Atoms and elements. Each element is made up of atoms with a specific number of protons, which defines the element, e.g., carbon, oxygen, nitrogen. The periodic table organizes elements based on their atomic number and properties. Molecules. Molecules are formed when 2 or more atoms bond together. 4. Example: a water molecule, HO, consists of 2 hydrogen atoms and 1 oxygen atom. Isotopes. Some elements have isotopes, which are atoms with the same number of protons but different numbers of neutrons. Isotopes can be stable or radioactive, and their behavior is important in tracing environmental processes. Electron configuration, the arrangement of electrons around an atom's nucleus, determines its chemical reactivity. Electrons in the outermost shell, valence electrons, are involved in chemical bonding. Chemical bonds. Atoms combine to form molecules through chemical bonds. There are 3 main types. O covalent bonds, formed when atoms share electrons, e.g., HO, CO. O ionic bonds, formed when one atom donates an electron to another, creating charged ions that attract each other, e.g., NaCl. O metallic bonds. In metals, atoms share electrons freely, creating a sea of electrons that gives metals their properties. Understanding atomic and molecular structures helps explain the behavior of chemicals in the environment, such as their ability to dissolve in water, how they bond to other substances, or how pollutants can accumulate in ecosystems. 2.2 Chemical reactions and bonding. Chemical reactions involve the breaking and forming of chemical bonds between atoms and molecules. These reactions are essential in environmental processes, such as the cycling of nutrients or the breakdown of pollutants. Types of chemical reactions. O. Combination reactions, two or more substances combine to form a new compound, e.g., 2H plus O2HO. O. Decomposition reactions, a single compound breaks down into simpler substances, e.g., HOHO plus O. O. Redox reactions, involves the transfer of electrons between substances. This is key in processes like respiration, photosynthesis, and the degradation of pollutants. O. Acid-base reactions, involves the transfer of protons, H ions, between substances. The pH of water, for example, affects the solubility and toxicity of many chemicals. O. Precipitation reactions, when two solutions are mixed, and an insoluble product, precipitate, forms. This is important in wastewater treatment and soil chemistry. Reaction rates. The speed at which a chemical reaction occurs depends on factors like temperature, concentration of reactants, and the presence of catalysts. Understanding reaction rates is crucial for predicting how quickly pollutants will degrade or how long they will persist in the environment. 2.3 Thermodynamics in environmental chemistry. Thermodynamics is the study of energy and its transformations. In environmental chemistry, thermodynamic principles help understand how energy changes during chemical reactions and physical processes, and how this affects the environment. First law of thermodynamics: energy cannot be created or destroyed, only converted from one form to another. This is important for understanding processes like the combustion of fossil fuels or the conversion of solar energy in photosynthesis. Second law of thermodynamics: the total entropy, disorder, of an isolated system always increases over time. This concept explains why some chemical reactions are spontaneous, they increase the system's entropy, while others require an input of energy. Gibbs free energy, delta G. This quantity indicates whether a reaction is thermodynamically favorable. If delta G is negative, the reaction is spontaneous. It helps determine the feasibility of chemical processes, such as pollutant degradation or the formation of ozone. Enthalpy, delta H. Enthalpy refers to the heat content of a system. Reactions that release heat, exothermic, or absorb heat, endothermic, can significantly influence the environment, e.g., climate change, ocean acidification. Thermodynamics is essential for understanding how pollutants behave in the environment. How energy is used or lost in chemical processes, and how reactions can be controlled or driven for sustainable purposes. 2.4 Kinetics and environmental processes. Kinetics is the study of the rates at which chemical reactions occur and the factors that influence those rates. In environmental chemistry, reaction kinetics helps us understand how fast chemicals are transformed or degraded in the environment. Reaction rate, the rate at which reactants are converted into products, is determined by the concentration of reactants, temperature, and the presence of catalysts. For example, the rate at which a pollutant decomposes in water depends on these factors. Environmental processes. Biodegradation, the breakdown of organic pollutants by microorganisms. Kinetic studies help assess how fast pollutants like oil or plastics degrade in natural systems. Atmospheric chemistry, reactions in the atmosphere, such as those involving greenhouse gases, ozone formation, and pollutants, are influenced by factors like sunlight, photochemical reactions, and temperature. Water treatment, kinetics are critical in understanding how contaminants are removed from water, including chemical reactions in processes like chlorination or oxidation. Soil chemistry, chemical reactions in soil, such as nutrient cycling or the movement of contaminants, are governed by reaction rates, affecting agricultural practices and environmental remediation strategies. Understanding kinetics is crucial for modeling environmental processes, predicting pollutant behavior, and developing strategies for cleaning up contaminated environments. Together, these basic concepts in chemistry form the backbone of environmental chemistry, providing insight into how chemicals move through and interact with natural systems, and offering solutions for minimizing environmental impacts and promoting sustainability. Composition of atmosphere. The Earth's atmosphere consists of nitrogen, oxygen, carbon dioxide, and other trace gases essential for life. Air pollution effects. Air pollution results from human activities and natural processes, impacting health and the environment. Greenhouse gases. Greenhouse gases trap heat in the atmosphere, leading to global warming and climate change. Ozone depletion. Ozone depletion occurs due to chemicals like CFCs, resulting in increased UV radiation reaching Earth. Major components. The atmosphere consists mainly of nitrogen and oxygen, which are crucial for life on Earth. Trace gases. Trace gases play a significant role in the atmosphere, despite their low concentrations. Air quality impact. Understanding atmospheric composition is vital for assessing air quality and the impact of pollutants. Sources of air pollution. Air pollution originates from both natural and human-made sources, such as industrial emissions and vehicle exhaust. Impact on human health. Air pollution poses significant health risks, contributing to respiratory diseases and other health problems in humans. Environmental effects. Air pollution negatively affects the environment, leading to issues such as climate change and ecosystem damage. Monitoring and management. Effective monitoring and management strategies are essential to mitigate air pollution and protect health and the environment. Point 3. The Earth's atmosphere and chemistry. 3. The Earth's atmosphere and chemistry. The Earth's atmosphere is a critical component of the planet's environmental system. It not only provides the air necessary for life but also plays a key role in regulating temperature, protecting organisms from harmful solar radiation, and supporting processes like the water cycle. Environmental chemistry explores the composition, behavior, and changes in the atmosphere, particularly in relation to air pollution and climate change. 3.1 Composition of the atmosphere. The Earth's atmosphere is made up of a mixture of gases that envelop the planet. The primary components include nitrogen, and the most abundant gas, making up approximately 78% of the atmosphere. Nitrogen is inert under normal conditions and does not readily react with other substances. Oxygen, comprising around 21% of the atmosphere, oxygen is vital for respiration and combustion. Argon, a noble gas, making up about 0.93% of the atmosphere, with very limited reactivity. Carbon dioxide, CO, although it makes up only about 0.04% of the atmosphere. CO is crucial for regulating Earth's temperature through its role in the greenhouse effect. Water vapor, HO. The amount of water vapor varies significantly, from 0 to 4%. And it is important for weather patterns and the water cycle. Trace gases, this category includes methane, CH, ozone, O, nitrous oxide, NO, and others, each present in small concentrations but playing significant roles in atmospheric chemistry and climate processes. In addition to these gases, the atmosphere contains particulate matter, e.g., dust, smoke, and aerosols, which can affect air quality and weather patterns. 3.2 Air pollution, sources and effects. Air pollution is the presence of harmful substances in the atmosphere, often as a result of human activities. These pollutants can have serious health, environmental, and climatic consequences. Sources of air pollution. Natural sources, volcanic eruptions, wildfires, dust storms, and biological processes like methane emissions from wetlands. Anthropogenic sources. Small black square transportation, vehicles emit carbon monoxide, CO, nitrogen oxides, NO, hydrocarbons, and particulate matter. Small black square industry, factories, power plants, and refineries release sulfur dioxide, SO, nitrogen oxides, NO, carbon dioxide, CO, and particulate matter. Small black square agriculture, livestock produce methane, and fertilizers release nitrous oxide, NO, a potent greenhouse gas. Small black square residential heating, burning wood or coal in homes generates particulate matter and carbon monoxide. Effects of air pollution. Human health. Pollutants like particulate matter, ground-level ozone, O, and carbon monoxide can cause respiratory problems, cardiovascular diseases, and other health issues. Ecosystem damage. Pollutants like sulfur dioxide and nitrogen oxides can acidify soils and water bodies, damaging plant life, aquatic ecosystems, and biodiversity. Visibility reduction. Smog and haze from pollutants reduce visibility and affect aesthetic and environmental quality. Climate change. Some pollutants, like black carbon and methane, contribute to warming by absorbing sunlight and increasing the greenhouse effect. The complexity of air pollution lies in the way pollutants interact with each other and the environment. Some pollutants have a direct effect, e.g., smog formation, while others lead to more complex consequences, like acid rain or climate change. 3.3 Greenhouse gases and global warming. The greenhouse effect is a natural process that warms the Earth's surface. Greenhouse gases, GHGs, trap heat from the sun, preventing it from escaping back into space. However, human activities have increased the concentration of these gases in the atmosphere, leading to an enhanced greenhouse effect and global warming. Greenhouse gases. Carbon dioxide, CO, the most significant human-caused greenhouse gas. Primarily produced by the burning of fossil fuels, e.g., coal, oil, and natural gas, for energy, transportation, and industrial processes. Methane, a more potent greenhouse gas than CO. Methane is released by livestock, landfills, wetlands, and the production of oil and gas. Nitrous oxide, NO, produced by agricultural practices, especially the use of synthetic fertilizers, as well as industrial processes. Fluorinated gases, synthetic gases used in refrigeration, air conditioning, and industrial processes, including hydrofluorocarbons, HFCs, perfluorocarbons, PFCs, and sulfur hexafluoride, SF. These gases are potent greenhouse gases with long atmospheric lifetimes. Impacts of global warming. Rising temperatures, increased greenhouse gas concentrations lead to higher global temperatures, which affect weather patterns, ecosystems, and human societies. Melting ice and rising sea levels. Warmer temperatures cause polar ice sheets and glaciers to melt, contributing to rising sea levels and threatening coastal communities. Changes in precipitation. Global warming can lead to altered weather patterns, including more frequent and intense storms, droughts, and flooding. Ocean acidification. Increased CO absorption by the oceans lowers the pH, negatively affecting marine life, particularly coral reefs and shellfish. Efforts to mitigate global warming focus on reducing greenhouse gas emissions, transitioning to renewable energy sources, and enhancing carbon sequestration through reforestation and carbon capture technologies. 3.4 Stratospheric ozone depletion. The ozone layer, located in the stratosphere, plays a critical role in protecting life on Earth. By absorbing most of the sun's harmful ultraviolet, UV, radiation. However, human-made chemicals have caused damage to this protective layer, leading to ozone depletion. Ozone depletion mechanism. The depletion of ozone is primarily caused by human-made chemicals called ozone-depleting substances, ODs, especially chlorofluorocarbons, CFCs, halons, and other halogenated compounds. When released into the atmosphere, CFCs and similar chemicals slowly rise to the stratosphere, where ultraviolet radiation breaks them down, releasing chlorine, Cl, and bromine, Br, atoms. These halogens then catalytically destroy ozone molecules, O, converting them into oxygen molecules, O, and individual oxygen atoms, O. A single chlorine or bromine atom can destroy thousands of ozone molecules before being removed from the stratosphere. Consequences of ozone depletion. Increased UV radiation. Ozone depletion leads to higher levels of harmful UVB radiation reaching the Earth's surface. This can cause skin cancer, cataracts, and weakened immune systems in humans, as well as disrupt ecosystems, including marine plankton and crop growth. Changes in climate, ozone depletion and the warming of the lower atmosphere, due to increased greenhouse gases, are interconnected. These changes can alter atmospheric circulation patterns and impact weather systems. Montreal Protocol. To address ozone depletion, international agreements like the Montreal Protocol have been successful in reducing the use of ODs. Since the protocol's implementation, there have been signs of gradual recovery in the ozone layer, although full recovery will take several decades. Understanding the chemistry of the atmosphere is crucial for tackling global environmental challenges such as air pollution, climate change, and ozone depletion. Efforts to address these issues require international cooperation, technological innovation, and sustainable practices to protect the Earth's atmosphere and ensure a healthy planet for future generations. The water cycle. The water cycle is a continuous process that describes the movement of water through evaporation, condensation, and precipitation. Impact of pollution. Pollution significantly affects water quality, impacting ecosystems and human health by introducing harmful contaminants. Chemical contaminants. Chemical contaminants in water can disrupt aquatic ecosystems, leading to biodiversity loss and health risks for organisms. Evaporation process. Evaporation is the process where water is converted from liquid to vapor, rising into the atmosphere. Condensation formation. Condensation occurs when water vapor cools and changes back into liquid, forming clouds in the sky. Precipitation mechanism. Precipitation is the release of water from clouds in the form of rain, snow, sleet, or hail. Runoff importance. Runoff is the process where water flows over land, replenishing rivers, lakes, and groundwater supplies. Causes of water pollution. Water pollution is caused by various contaminants such as chemicals, waste, and pathogens entering water bodies, which harms ecosystems and public health. Impact on ecosystems. Contaminated water disrupts aquatic ecosystems, leading to loss of biodiversity, altered habitats, and negative health effects on wildlife. Water treatment methods. Implementing effective treatment methods is crucial for restoring water quality, ensuring safe drinking water, and protecting public health. Point 4. Water and its chemical properties. 4. Water and its chemical properties. Water is essential for life and plays a critical role in Earth's environmental systems. Its unique chemical properties make it a vital solvent, medium for chemical reactions, and regulator of temperature. In environmental chemistry, understanding water's behavior, contamination, and treatment is crucial for maintaining healthy ecosystems and human societies. 4.1 The water cycle. The water cycle, also known as the hydrological cycle, is a continuous process through which water circulates between the Earth's surface and the atmosphere. It involves several key processes that help maintain the availability of water across the planet. Evaporation. Water from oceans, lakes, rivers, and other bodies of water turns into vapor and rises into the atmosphere. Plants also contribute to this process through transpiration, collectively called evapotranspiration. Condensation. As water vapor rises and cools, it condenses into liquid water, forming clouds. Precipitation. Water falls from clouds in the form of rain, snow, sleet, or hail. Infiltration and runoff. Some of the water seeps into the ground, infiltration, to replenish groundwater supplies, while the rest flows overland, runoff, into rivers, lakes, and oceans. Groundwater. Water that has infiltrated the soil is stored underground in aquifers. This water can eventually resurface through springs or be accessed via wells. The water cycle is essential for replenishing fresh water supplies and regulating the distribution of water across different ecosystems. It also helps distribute heat around the planet, contributing to climate regulation. 4.2 Water pollution and treatment. Water pollution occurs when harmful substances, such as chemicals, pathogens, or waste products, are introduced into water bodies. It threatens human health, wildlife, and ecosystems. Pollution can be classified into two main types. Point source pollution, pollution that originates from a specific, identifiable source, such as a wastewater discharge from factories, sewage treatment plants, or oil spills. Non-point source pollution, pollution that comes from diffuse sources, such as runoff from agricultural fields, urban areas, and construction sites. It often contains pesticides, fertilizers, heavy metals, and other contaminants. Treatment of polluted water. Water treatment is necessary to remove contaminants and make water safe for drinking, irrigation, and other uses. Water treatment typically involves several stages. 1. Coagulation and flocculation. Chemicals are added to water to form small particles, floc, that bind with impurities. 2. Sedimentation. The floc and contaminants settle to the bottom of the tank due to gravity. 3. Filtration. Water is passed through filters, e.g., sand or charcoal, to remove remaining particles. 4. Disinfection. Chlorine, ozone, or ultraviolet light is used to kill remaining pathogens and bacteria. 5. Advanced treatment. Some contaminants, such as heavy metals, pesticides, or pharmaceuticals, may require additional treatments, such as reverse osmosis or activated carbon filtration. Wastewater treatment also includes processes to treat industrial effluents, sewage, and agricultural runoff, often involving biological treatment, e.g., activated sludge processes, to break down organic matter. 4.3 Chemical contaminants in water. Various chemical pollutants can contaminate water sources, and they can have serious impacts on water quality, human health, and ecosystems. Heavy metals, toxic metals like lead, Pb, mercury, Hg, arsenic, As, and cadmium, Cd, can enter water sources through industrial discharges, mining operations, and improper waste disposal. These metals can accumulate in aquatic organisms, leading to bioaccumulation and biomagnification, and can be harmful to both humans and wildlife. Pesticides and herbicides, chemicals used in agriculture to control pests and weeds, often end up in water bodies through runoff. These chemicals can contaminate drinking water supplies and harm aquatic life by disrupting ecosystems and causing algal blooms. Nutrients, nitrogen, N, and phosphorus, P, are essential for plant growth but can become pollutants when present in excess. They often enter water from agricultural runoff, fertilizers, wastewater effluents, and animal waste. Excess nutrients can cause eutrophication, leading to oxygen depletion, fish kills, and harmful algal blooms. Pharmaceuticals and personal care products, PPCPs, trace amounts of drugs, hormones, and personal care products can be found in water due to improper disposal, wastewater treatment limitations, and agricultural use of veterinary drugs. These substances can affect aquatic life and may contribute to antibiotic resistance. Organic pollutants, volatile organic compounds, VOCs, like benzene, trichloroethylene, and solvents from industrial and household sources can contaminate water. They can pose carcinogenic and toxic risks to humans and wildlife. Radionuclides, radioactive materials, such as radon or uranium, can enter water sources through natural processes or industrial activities like mining and nuclear waste disposal. Managing and monitoring these contaminants is critical to maintaining water quality and ensuring the health of ecosystems and people who rely on water resources. 4.4 Acid rain and its environmental impact. Acid rain refers to any form of precipitation, rain, snow, sleet, fog, that has a pH below 5.6. Primarily due to the presence of sulfuric acid, HSO, and nitric acid, HNO. These acids form when sulfur dioxide, SO, and nitrogen oxides, NO, released by burning fossil fuels, e.g., coal, oil, and gas, react with water vapor in the atmosphere. Formation of acid rain. 1. Sulfur dioxide, SO, emitted from industrial processes, power plants, and transportation. In the atmosphere, SO reacts with oxygen to form sulfur trioxide, SO, which then reacts with water to form sulfuric acid, HSO. 2 nitrogen oxides, NO emitted by vehicles, power plants, and agriculture. Nitrogen oxides combine with water to form nitric acid, HNO. Environmental impacts of acid rain. Soil acidification. Acid rain can lower the pH of soils, disrupting the availability of nutrients and minerals needed for plant growth. It also releases toxic metals like aluminum, which can harm plant roots and aquatic organisms. Water quality. Acid rain lowers the pH of water bodies, such as rivers and lakes, making them acidic. This harms aquatic life, particularly fish and amphibians, which have narrow pH tolerance ranges. Vegetation damage. Acid rain directly damages plant leaves and stems, impairs photosynthesis, and weakens plant defenses, making them more susceptible to disease and environmental stress. Buildings and structures. Acid rain accelerates the degradation of buildings, monuments, and infrastructure made of limestone, marble, and other stone materials by reacting with the minerals and causing erosion. Mitigation. Reducing emissions of sulfur dioxide and nitrogen oxides through regulations, cleaner technologies, and the use of cleaner fuels has been effective in reducing acid rain. The Clean Air Act in the U.S. and similar regulations worldwide have contributed to significant reductions in acid rain. In summary, water is a vital and dynamic component of the Earth's systems, and understanding its chemical properties is essential for addressing water quality issues, pollution, and the broader environmental impacts such as acid rain. Environmental chemistry plays a key role in devising solutions for water treatment, pollutant management, and the conservation of water resources. Soil composition. Understanding soil composition is crucial for identifying contaminants and assessing soil health. Different minerals and organic matter impact soil properties. Soil pollution. Soil pollution refers to the presence of harmful substances in the soil, which can lead to environmental and health issues. Remediation techniques. Various remediation techniques can restore polluted soil, including bioremediation, phytoremediation, and soil washing. Consequences of soil degradation. Soil degradation can lead to reduced agricultural productivity, loss of biodiversity, and increased pollution in water systems. Components of soil. Soil is composed of minerals, organic matter, water, and air, all of which are essential for its functionality. Soil structure. The arrangement of soil particles and the spaces between them define the soil structure, influencing water retention and root penetration. Impact on plant life. Soil composition and structure greatly affect its capacity to support plant life and overall ecosystem health. Soil as a filter. Soil acts as a natural filter, helping to cleanse water by trapping pollutants and improving water quality. Sources of soil contamination. Soil can become contaminated through various sources, including heavy metals, pesticides, and industrial waste products. Bioremediation techniques. Bioremediation utilizes living organisms, such as bacteria and fungi, to detoxify and restore polluted soil environments effectively. Phytoremediation methods. Phytoremediation involves using plants to absorb and remove contaminants from the soil, offering a natural solution to pollution. Point 5. Soil chemistry and pollution. 5. Soil chemistry and pollution. Soil is a fundamental component of terrestrial ecosystems, supporting plant growth, regulating water flow, and providing habitat for organisms. Soil chemistry is essential for understanding how nutrients, contaminants, and other substances interact within the soil, and how pollution can degrade soil health and function. In this section, we explore soil composition, contamination, and remediation, as well as the consequences of soil erosion. 5.1 Soil composition and structure. Soil is a complex mixture of mineral particles, organic matter, water, and air. Its composition and structure determine its ability to support plant growth and perform ecological functions. Mineral components. These include sand, silt, and clay. The relative proportions of these particles determine the soil's texture. Sand, coarse and large particles, drains water quickly, but has low nutrient holding capacity. Silt, fine particles, holds water and nutrients better than sand. Clay, very fine particles, retains water and nutrients well but has poor drainage. Soils are classified based on their texture, such as sandy, loamy, or clayey soil. Organic matter, decomposed plant and animal material, also known as humus, contributes to soil fertility by providing nutrients and improving soil structure. Organic matter enhances the soil's water-holding capacity and supports microbial life. Soil pH, which measures the acidity or alkalinity of the soil, influences nutrient availability. Most plants thrive in soils with a pH between 6 and 7, neutral, though some may prefer more acidic or alkaline conditions. Soil fertility. Fertility is determined by the availability of essential nutrients, e.g., nitrogen, phosphorus, potassium, and the soil's ability to retain and release these nutrients. Soil organic matter and microbial activity play a crucial role in nutrient cycling. Soil structure, the arrangement of soil particles into aggregates, which determines the soil's porosity and permeability. Well-structured soil has good aeration and water infiltration, while compacted soil may hinder root growth and water movement. Soil composition and structure are key to understanding how pollutants interact with the soil, how contaminants are retained or leached, and how soil functions in sustaining ecosystems. 5.2 Soil contaminants and remediation techniques. Soil contamination occurs when harmful substances, such as heavy metals, pesticides, industrial chemicals, and petroleum products, are introduced into the soil. These contaminants can disrupt soil health, reduce agricultural productivity, and pose risks to Human and environmental health. Common soil contaminants. Heavy metals, lead, Pb, mercury, Hg, cadmium, Cd, arsenic, As, and chromium, Cr, are common pollutants from industrial, agricultural, and urban sources. Pesticides and herbicides, chemical compounds used in agriculture can persist in the soil and contaminate water supplies, affecting biodiversity and food safety. Petroleum products, spills or leaks from industrial or transportation activities can introduce hydrocarbons into the soil, harming plant and microbial life. Industrial chemicals, chemicals like solvents, polychlorinated biphenyls, PCBs, and other persistent organic pollutants, POPs, can accumulate in soils, impacting ecosystems. Remediation techniques. Physical remediation involves removing contaminated soil or isolating pollutants. For example, contaminated soil can be excavated and replaced, or treated in situ with technologies like soil washing, washing soil with water, or solvents to remove pollutants. Chemical remediation, chemical treatments, such as oxidation or reduction, can break down or transform contaminants into less harmful substances. For example, the use of potassium permanganate to degrade organic pollutants in the soil. Bioremediation uses microorganisms or plants to degrade or absorb contaminants. Plants, phytoremediation, or bacteria, bioremediation, can absorb or break down pollutants like heavy metals, organic solvents, and petroleum products. Bioventing involves using oxygen or nutrients to stimulate microbial activity in the soil to degrade organic contaminants. Stabilization/solidification, contaminated soil is mixed with chemicals to immobilize harmful substances and prevent them from leaching into groundwater. Each remediation technique is tailored to the type of contamination, the scale of the problem, and the specific characteristics of the contaminated site. 5.3 Heavy metals and pesticides in soil. Heavy metals and pesticides are some of the most concerning soil contaminants because of their toxicity, persistence, and potential for bioaccumulation in food chains. Heavy metals, these elements are naturally occurring but can be introduced into soils through industrial activities, e.g., mining, smelting, manufacturing. Agricultural practices, e.g., pesticides, fertilizers, and urban pollution. Toxicity, many heavy metals, such as lead, mercury, and cadmium, are toxic to plants, animals, and humans. They can accumulate in plant tissues and enter the food chain, posing risks to human health. Bioaccumulation, heavy metals can build up in living organisms over time, leading to harmful effects, such as developmental and neurological damage in humans and animals. Mobility, some heavy metals can leach into groundwater, spreading contamination beyond the immediate area and affecting water quality. Pesticides, pesticides and herbicides are commonly used in agriculture to control pests and weeds, but they can persist in the soil for years, affecting microbial and Plant health. O persistence. Some pesticides, especially organochlorine compounds, are resistant to breakdown and remain in the soil for long periods, potentially harming non-target organisms. O ecosystem impact. Pesticides can disrupt soil microbial communities, which are essential for nutrient cycling and soil health, and can harm pollinators like bees, which are crucial for agriculture. Efforts to reduce heavy metal contamination and pesticide use include regulations on industrial emissions, the development of safer chemicals, and the promotion of organic farming practices that minimize chemical inputs. 5.4 Soil erosion and its environmental consequences. Soil erosion is the removal of the topsoil layer by wind, water, or human activity. Topsoil contains most of the soil's nutrients and organic matter, so its loss can degrade land and reduce agricultural productivity. Causes of soil erosion. O agriculture, improper farming practices, such as overgrazing, monoculture cropping, and plowing, can disturb the soil, making it more susceptible to erosion by wind and water. O deforestation, the removal of trees and vegetation reduces the soil's ability to retain moisture and protects it from wind and water erosion. O construction and urbanization, development of land for cities, roads, and infrastructure can disturb soil and increase runoff, leading to erosion. O climate change, increased rainfall intensity and wind patterns due to climate change can exacerbate erosion. Consequences of soil erosion. O loss of fertile soil. Erosion removes the topsoil, which is rich in nutrients and organic matter, leading to reduced soil fertility and crop yields. O water pollution. Eroded soil can carry sediments and pollutants, such as pesticides and fertilizers, into rivers and lakes, leading to water pollution and eutrophication. O desertification. In areas where erosion is severe, land may become barren and incapable of supporting plant life, contributing to the spread of deserts and the degradation of ecosystems. O reduced biodiversity. Soil erosion can lead to the loss of habitat for various species of plants, animals, and microorganisms that depend on the soil for survival. Prevention and mitigation. O erosion control practices. Measures such as contour plowing, terracing, planting cover crops, and creating windbreaks help protect soil from erosion. O reforestation. Planting trees and vegetation helps stabilize the soil and reduce the impact of wind and water erosion. O sustainable agriculture. Implementing sustainable farming practices, such as crop rotation, agroforestry, and reduced tillage, helps prevent soil degradation and erosion. In summary, soil chemistry plays a critical role in the function of terrestrial ecosystems and agriculture. The contamination of soil with heavy metals, pesticides, and other pollutants poses serious environmental and health risks, while soil erosion exacerbates land degradation and pollution. Effective management and remediation techniques are crucial for protecting soil health and maintaining ecosystem services. Importance of environmental chemistry. Environmental chemistry is essential for understanding complex environmental issues and their implications for life on Earth. Sustainable solutions. Studying atmospheric, water, and soil chemistry helps us create sustainable solutions to protect and preserve our environment. Future generations. Understanding environmental chemistry is crucial for ensuring a healthier planet for future generations to thrive.